Goal of today is to learn how to write, I guess I should add to this, reaction rate laws is what we're learning how to write out today, and then how to perform mathematical equations with them. Okay, your homework assignment is actually going to be fairly short compared to other days where it's a lot, but that's because I want you to spend some really good quality time making sure you understand this process. Okay, so the whole thing here is from experimental data. Remember, that's key. You cannot write a rate law without experimental data. You can't just write it from a reaction because you don't know how fast or what things are affected by just a chemical reaction. Okay? So last time I think we wrote this in, or at least we looked at one of the relationships. But what we're trying to see here is we're trying to see how each of our different reactants affects the rate. Okay, so I don't remember which two we compared.
It was 4 and 5. 4
and 5, thank you. So we looked at, okay, so yeah, so 4 and 5, maybe label this just in case. So this was constant.
Same.
Okay, one of the things has to be kept constant while we look at the other. And then we saw, okay, this doubled, and then the rate also times by 2. So it's a direct relationship for that particular one. Okay, now let's look at our other one. So let's find 2. So I'll just say, all right, so it looks like this is held constant. Okay, so we need to pick something where it's constant. So then I see, okay, from 1 to 2, this one times by 2. And then what happened to our rate law? Or I mean our reaction rate?
Times 2.
It also times by 2. Okay? So from this data, what we're able to write, and we'll do a few of these today. So if it's like piecing it together, you don't quite see it, just hang on, and I think you'll get a clear picture as we go. But we can write a rate law from that data that says this. Okay, a rate law is you always write the rate equals. Okay?
They got it.
We have this value k, which is our rate constant. We'll talk about that. Okay, and then for, I forgot what our reaction was. So we had NH4. Okay, so the concentration of NH4, and then our other reactant was NO2. Is it NH4 plus?
Yes.
Yeah.
Thank you.
It's an ammonium ion.
Okay, all right. So what we saw was because in our experiment, we saw that every time this doubled, the rate doubled. In a sense, you could write this in, but in the future you don't have to. That's why this is like to the power of 1, because they're directly related, right? So every time this doubles, that's going to double. Same thing, this would also be in a sense to the power of 1. Okay? We could have seen in our data that when it tripled, what would happen to the rate? It also tripled, right? So when the relationship is exactly the same change, it's always to the power of 1. And this equation shows, why did I leave that blank?
Yeah, you left the top one blank too. Is it reactants?
How the rate depends on the concentration of the reactant. It's called our rate law. Yeah, the top one's reactant. Okay, so this whole thing is my rate law. So when a problem says to write a rate law, you're not mathematically solving for anything yet. You are just showing the relationship of the concentrations and how they affect our rate. Okay, so this right here is a generic example of what a rate law will always look like. So you have rate equals your concentrations, and then you have these exponents, okay? K is the rate of our rate law. It's called the rate constant. Key thing here is the only thing that affects K is really our temperature. Catalyst can also change our K, but we'll get to that later. Okay. Okay. Our rate constant will only change if the temperature is changing. Otherwise, it is truly a constant. Okay? And then, like we said, our exponents are typically whole numbers. In this class, they will always be whole numbers because we won't get that in depth here. No, if you keep going further on, that they could get a little bit crazier. But for us, it's either going to be 0, 1, or 2. Okay? So, first off, what I can do is once I have a rate law, from that we can calculate what the value of K is since it's held constant. Okay? Man, I gotta stop saying that. Okay. All right, so I'm just going to rewrite our rate law so we have it right here to look at.
Say okay instead of okay.
Alright.
So we found this. Okay. Was it NO2? Yeah. So what we can do is we can just go to that ginormous table of data, and since my temperature is not changing between any of my trials, you could pick any one you want. Okay, so for example, I think I picked number 1 just because it's on top. But what I want to do here, just to prove a point, is everyone, so I'm going to show you for experiment 1. Everyone on the first row, you're going to do experiment 2. And then the next one, experiment 3, and experiment 4. So all we do, so you can look at your data with me. Okay, so for mine, my rate was 5.4 times 10 to the negative 7. And keep track of your units here. Right, so the second row, if you look at your data table, what was your rate?
10.8 times 10 to
Good, and then the next one, you guys are the 21.5, and then the last one, you guys are also 10.8. All right, we're solving for K, so you leave that as a variable. And then for my initials, I had 0.0100 and molarity and 0.200. So plug in the different ones, because we should, being that it's constant, we should all get the same K no matter what trial we pick.
Can I use my phone when the calculator died?
Yeah. You can also grab one too there if you want.
What's the
That's fine.
units on the amount of the different ions? Is that molarity?
That's what you think it is.
The concentrations?
Yeah.
Yeah, those are molarity.
Wait.
And then you can earn a smiley face if you can tell me the right units in the end too. So even if you don't have a calculator, write out the work, and then show me what your units of K should be. And then we'll check it, we'll compare with each other. So for this one, we're just going to
Flip
divide.
to the side, foolish calculator.
Wrong
Okay.
thing. Trying to get K all by itself. So I'll just divide my concentrations to the other side. When you have an answer, go ahead and put your pencil down so I know that we're ready to check it. So I'm just going to straighten that out.
The units for that.
You got the same.
Okay, does everyone have an answer?
Yes.
Okay, so I got, when I did trial or experiment 1, I got 2.7 times 10 to the negative 4.
What?
Same.
They're 4.
Did we get the same
I
answers?
got
Yes.
negative 5.
I got -5.
You got negative 5. My guess is maybe you missed like typing that 0.
Oh. Yep. I messed
You
up.
got negative 4.
Because
yeah,
it's
James?
Yeah.
Point 0. Austin. Because it's point 0.
I did no, I did 0.0.
You did.
Oh, so you got a key.
Okay, so I didn't.
I
Here's
did-
here's
I know, I
exactly
did.
what I calculator.
Because did your rate have 3 in it?
Yeah.
Oh yeah, it did, huh?
Zero.
So I guess technically you had what, 2.7?
It was 2.6.
Oh yeah. So yeah, that's true. If your rate had a little bit more sig
Oh, yeah.
figs, but in the end, mathematically, it is the same. But that is a good point. Okay, and then if you got these units, and there's 2 ways you could written it. You can have a smiley face. So the units of our K, we'll talk about it because they're a little weird, is you could write it as per molarity times seconds. Or, so write this on if you don't have it. The other way is whenever it's the inverse, you could have molarity, inverse molarity, inverse seconds. Because that means over.
I just wrote 1 over molarity seconds.
That's fine.
Okay,
Question. If that's how it was, then wouldn't the molarity cancel out? Oh wait, never mind.
No, it
That's
did
why
cancel
it
out.
So that's
There
the
was
thing. So
2
one
molarities.
of them did cancel, but we're left with another one still on the bottom.
Answer that question.
Okay? So the units of K we'll kind of talk about here. They're a little bizarre, but they also will change. It's not a set always this, because it depends on our concentrations and how many we have. So K's units are something you're always going to have to find in doing the process. We should be getting good anyways at just always doing units. But recognize that K is not just a unit you can just memorize. as a set way, nor would it be worth your time because it's going to change depending on our reaction. Yeah?
Do we need to know the units for K, because it's just kind of you find it and then you plug it in?
I mean, it's just always that thing once again of the units just help make life a full puzzle. You know what I mean? Like, yes, in the end, if your units of K are correct, so on this next one here, everybody, so now what we're doing, so I have my K, so with my rate law, so I'm going to just rewrite it here. So now I know that the rate is equal to 2.7 times 10 to the negative 4, and then times whatever the concentrations are. So here's why rate laws are beneficial. Is in the beginning we had to do some sort of experiment to get this data. But once I get enough data, now I can just use math to find any rate I want. Right? So I don't have to actually go into the lab and do these initial concentrations. I can just plug them into my equation and find the rate. So that's why the rate law helps us. It's kind of a weird cycle, I guess. You have to get data to get a rate law, but then once you have the rate law, you don't have to get any more data because it gives it to you, right? So in this one, we just want to know what is the rate if these are my initial concentrations. So you simply would plug these in to here and then work it out, right? So in the end, I guess we just move our decimal. So it's 2.7 times 10 to the negative 6.
Yep.
If you track your units, right, the units of both of these are molarity, right? Keep a difference here because it could affect something. So this is capital M, this is capital M. So we do cancel off the molarity there on the bottom, and so I'm left with, which for a rate, does that make sense? Yeah, right? So molarity per second is how we measure all rates of reaction. So the K should always work out unit-wise to cancel everything except for molarity per second. Okay? So 3-step process here, and that you'll repeat on the homework, and we'll do another example. You find the rate law. You then find K, and then you can find whatever other rate you want, basically, by just plugging it into your equation.
As long as it's the same temperature.
As long as we haven't changed the temperature. Good point, Spencer. All right, so let's talk a little bit more about these exponents here. So we call these things the reaction order. For example, in the one, oh, let's get rid of this mess. So the way we would classify this is because the exponent is a 1, we call this first order in respect to this. It would also be first order in respect to our nitrate, because the exponent defines what the order is. Okay? We can also have, though, is we can have an overall order, which is simply just the sum of all the individuals. So for the one we just did, overall, we would classify it as a second order reaction. So notice individually, they're both first order. As a whole reaction, we would classify it as second order. Okay? With this, once again, as we looked at our data, we see that it was raised to the power of 1 because the rate doubled when NH4 doubled, right? It's not about the double, it's about it's the same. It could triple, quadruple, whatever. Okay, the other types of orders we have are if the rate law is second order, what that means is that if by chance the concentration doubled, the rate now quadruples. Because think of it to the power of 2. Okay, now you gotta think carefully here. What if in my data, let's say my concentration, let's say I tripled it. What would happen to my rate if it was second order? Yeah, because keep in mind that we're squaring, so it would by 9.
It would non-tuple.
What? Non-tuple.
Yeah.
I guess so.
Ninefold. It said ninefold.
Okay, so just kind of recognize that relationship here. All right, so let's look at a few examples. Take your pencil here and let's write some things off to the side of these.
Isaac, what's the blank?
Let's do this. Let's force some smiley faces here.
Isaac, the first
Off to the side of these example equations.
first blank.
Write what is the overall rate order for each of these three reactions.
Right there.
Okay? So write down what is the overall rate order for each of these three reactions. You can have a smiley face for each one you get correct. Okay, ready? Show me with your fingers what is the overall rate order for this reaction. Show me with your fingers. Good. Parker in the back, why is it first order?
Because the N2O5 is just to the 1.
Yeah, so there's only one reactant and it's just, there's no exponent, which means it's just one. Okay? Notice, once again, and maybe write an extra star here. This rate law, how did I find this? Experimental data. Okay? Notice, in the equation, there's a 2 here. That has nothing to do with this. Okay? Don't confuse the two, because sometimes it can look like it came from an equation, because it happens to be the same. But rate laws always come from experimental data. Okay? Okay, show me the next one on your fingers. What do you think that one is?
1 second.
Yeah, you gotta be creative here.
I don't want to put it on.
All right, if you're trying to show me 1.5, you are correct.
Yeah.
Because once again, that's to the 1. This would be first order with respect to this, half an order with respect to that. It's the total 1.5. And last but not least, show me what you think on the last one. What's our rate order? Very good. You can have a smiley face for each one you got right. And Parker, you can have a bonus for helping us out. Okay? But like I said, in case you didn't hear the third time I told you, experimentally is how these things are determined.
That's a sick beat right
Say
there.
what?
That's a fire beat.
I have.
I'm sorry, Paul, I didn't
I
catch
have
that.
more
one.
smiles.
We're on the quiz next time. Where does that come from?
I didn't do the
Yeah. We're gonna do it. And it's gonna be 100 points.
Choose the last
Yep. Okay,
Remember.
now let's look at a little bit more at K here, everybody. Give me your attention. So, this is obviously just a general rule, but a large value of K, and that's supposed to be an exponent. I think it's an exponent in your notes. Does it say 10 to the 9th?
Yeah, I think it does.
Okay, not 109. Okay, so if your K is large or above 10 to the 9, we would consider that fast.
What is that right here?
Versus if it's really small, then it would be considered slow. Once again, fast and slow are all relative in what you're comparing to. But in general, K can be used to without plugging anything in to say how fast or slow a reaction is going. Okay, we talked about before that the units of our constant depend on the overall reaction order. So they're going to change depending on what we did. In general, we know that if, let's say, it was a first, let's say if it's a first order reaction here, right? Then what that would mean is I have some rate. So put this in that little box.
The old chemicals die. Kill them if you have to.
We have K, and then if it's first order, that means you just have one thing to the power of 1, right? So just for simplicity's sake, we're just going to say A. Which means for units of our K, what is concentration always measured in? Molarity. And rate is always measured in?
So would it just be per second?
Molarity per second. So if I isolate K by itself, right, we're basically going to take the rate divided by the concentration of A, which if rate is molarity per second and concentration is just molarity, then my unit for a first order reaction is just per second.
And then
Or you'd write like this, inverse seconds.
And then as you add orders, every order you add adds the molarity to the bottom.
Very
of
good,
that.
yeah, so then as we get higher and higher in our different orders,
Like,
So wait,
then those
So,
units.
like,
is that a
16th
first order
order
one
would
or is
be-
that a?
So this is first order.
So what would zero be?
Molarity per second.
Because if it's zero order, then technically you just have the rate equals K, right? So yeah, it'd just be molarity per second. Yeah, James and Spencer.
On the back page, you had one that had
The reaction
the
just
0.5.
exists.
The raised to the 0.5. If you
Yeah.
had 2 raised to the 0.5, would it still work out to be seconds? Okay.
So if you had two things, so the overall it's still first order.
Overall, is still first order.
Mhm. Yeah, if it's overall first order, it will always be this. So yeah, Spencer.
And so if you had like a 16th order reaction, it would be seconds to the -1 and molarity to the -15.
Yep.
Well,
there you go.
Does that exist?
I don't know.
So if
Let's do the second order one real quick in that next box. I think I skipped it. Do you have a box where it says second orders?
I have
Yeah.
Oh,
Xbox.
yeah.
So for second order, that means technically there's different ways in which something can be overall second order.
Get PC.
You can either have one thing
I place of 5.
that's second order, or you could have two things that are both first order, right? But if we just look at it this way, once again, if I'm isolating K, I have the rate divided by now the concentration squared.
Great.
So now we have molarity per second over molarity squared. So once again, in the end, that would give me either per molarity times seconds, or you can write it as the inverse style.
Inverse style
They mean
is
the same
what?
thing, so just recognize that. All right, so let's practice again on how to use these rates to find a rate law. Okay? So with working with rate laws, once again, notice that the rate depends on the concentration, but the rate constant does not. The only thing that can affect K is temperature
And catalyst.
and catalyst. So concentration will not change that K value, only temperature or catalyst.
By the present.
All right, so let's look at this data and see what we can decode. Let's do this. Let's have you try with your table buddy and see if you can find for me for A and B, are they zero order, first order, or second order? So once again, you need to compare the data. So I'll get you started, right? So I would notice that this is constant. Notice how that changes, and then what happens to the rate, and that should tell you the rate order. This one was constant, right? This one was easy in the sense that there wasn't tons to compare. But if there's lots of trials, make sure that you're keeping one thing constant in what you're comparing, because otherwise it will really mess up your math. Right? So we saw that this one doubled, but the rate did not change, which means that in respect to A,
Shooketh.
it is zero order.
Wait, B.
I mean B. I was testing all of you. Good job. Okay, so yeah, because we were in column B. So now I'm going to compare, because I want to keep B constant. So from here to here, that stayed constant. Here to here, it doubled. And this one quadrupled, which means its rate order is
To the second.
2. Okay?
Dose.
Technically, since it's to the zero order, you can simplify it
That's 1.
to just that.
Get
But it's
freaking
good
right.
to think through that process.
Why does it even mention B? Because
Yeah, like-
if B is of the 0 order, then it's not needed.
How does that even work?
All right, tell me this.
It's for notations.
The amount
Does-
of B does not affect the rate at all.
Is B necessary for this reaction to occur?
Yes.
Definitely.
Yeah.
Yeah, it's part of the reaction, but what is it not affecting? The rate. Right, so the concentration of B doesn't make it go faster or slower,
It changes the outcome.
but you gotta have B, otherwise you have no reaction, right? So keep in mind that this is about the speed at which it's going. So that was a good thing to
So like,
think about.
I'm
not gonna go to the next slide so we can keep our data up here. So there's part A, is we found the rate law. Part B now says find the magnitude of K. So we're just trying to find what is the actual value of our rate constant like we did before. So does it matter which trial I pick?
Nope.
Nope, so pick any trial you want. I'm gonna pick the first one. So my rate is 4.0 times 10 to the negative 5th. Right, is equal to K times the concentration of A squared.
What did you
What?
get for your answer?
And then solve for K. Alright, so to find K, once you have a rate law, you just plug that in. You get 4.0 times 10 to the negative 3.
It's 4 times 10 to the negative 7.
Yes. Watch.
And once again, if you track your units, or if you remember, because it is second order overall,
Oh.
No, it's not.
it would
It's
be
three.
Yeah.
molarity
Because division.
times seconds.
Unless
My name is division. I ruin everything.
Okay, questions on finding K?
MSP.
And then finally, C is now it just wants to know what would be the rate if I now used these concentrations.
When did?
So you can just plug those in to your rate law with your K. Right, so I have rate equals my K I just found times the concentration of A squared. B doesn't matter. And then we would find that the new rate for this example is 1.0 times 10 to the negative 5 molarity per second.
Oh.
Questions on that? Yeah, Annalie?
So what would a free response question like this look like? Would they just have us do those three, or would they have us like find the molarity of the substances as well?
Like a free response could look very similar to this for sure. In finding a rate law, finding a K, and then plugging in some sort of data. And then there could be some sort of explaining different things. But yeah. So we'll look at some free response ones for this chapter later on. So great question. All right, so then the other way too, guys. So that's one way. So in this chapter, we're going to see there are 3 ways in which you can find the rate order. The first way, I mean, they all come back to experimental data of some sort. But you can also find rate orders by graphing their rate, the data that you get. And we'll do this on a homework assignment next time, I think, like a dry lab. So we're not going to get into it mathematically. If you want to on your own, that's fine. But what we can do is if you integrate a rate law, okay, so once again, if integration makes your heart freak out, it's fine. We're not truly integrating here because I'm just giving you the answer. Okay, we can get this equation. So it's the natural log, so ln, you read it in cursive typically. Okay, the natural log of the concentration of A at some time, so little t is time, minus the natural log of the concentration of A at time 0, so like when I began, and that equals negative kt. What this equation does, I'll leave it up there, but I'm just going to the next slide here, is this equation helps us do 3 things, or you can do 3 different things with it. Is 1, we can determine the concentration of the reactant remaining at any given time. So if I want to know, okay, after 30 seconds, how much am I going to have left? That's what this equation can show us. Okay? It also can show us the time it takes to get to a certain amount. right? Like, okay, well, how long will it take to only have 20 grams left? You can also use this equation. And then finally, also the time required to fall to a certain level. Yeah, fun.
Is there a proof to that equation, or is it just a, hey, it's there, use it?
Like how it was derived?
Yeah.
So yeah, if you know how to integrate, you integrate the rate law itself, and that's what you get. I don't know, I forget when you cover integration.
Calculus. It's calculus.
But I can't remember if have you covered it yet already in the year? Yeah? So that's how it is. I think the book, I don't even know if the book goes
The book
to
is like,
integration.
this is derived via calculus.
that
It's
all it
really
says?
hard. and confusing.
So if I integrate a second order, everybody, we get this. 1 over the concentration of A at some time is equal to KT plus 1 over the concentration of A at our initial time. I guess I didn't note this. The first equation we wrote for first order, the integrated one, that is on your formula sheet. You don't have to memorize that big theme. We'll just practice knowing how to use it. To be honest, this one is not on your formula sheet, which in my book means you won't ever have to use it.
Oh.
But as far as I know, the AP test really doesn't ever have you the ones you memorize aren't like really complicated. So, and then everyone have that one?
Is the LN one on your formula sheet?
So the ln one is the one that's on there. Okay, and then 0 order is the concentration of A at a given time equal to negative KT plus A at our initial time. Once again, remember that with 0 order reactions, A is independent in terms of affecting it, right? Alright, you want to take your pencil here, and you need to draw or highlight a box around this right here. Straight line plot.
You kind of already
You
you bullet
need.
those lines.
Did I bullet
Yeah.
for you?
You,
Oh, good.
you also included the slope.
Okay, so right on that, you need to memorize that. That is the one thing where it can be like this should be a freebie multiple choice question. Because I've seen it where they will give you graphs, and they'll say, based on this graph, is it first order, second order, or 0 order? Something like that. It's a multiple choice question. And it's based on
And then the third one is none of the above, right?
this. Something like
Fourth
that,
one.
probably. Right? Okay, it will be a straight line, and we'll label.
What does it mean versus time?
So it's like your X and Y axis.
Against time.
Basically, it's y equals that.
So let me show you the graphs, and maybe it'll make sense. Okay?
So like the line.
So here's our different graphs. So this one is graphing time versus 1 over concentration. So what if it's a straight line, what order is this one?
Second.
Second order. Good, Lizzie. Have a smiley face for that.
Oh.
Okay, so that would be a second order reaction. So these are 3 different reactions here. Because this one is straight, and I'm graphing time versus the natural log of A. So that would be first order. And then this is time versus concentration. It's just 0. So based on what shows up as a straight line, you can see what order it is. So on a dry lab, that you'll do is I'm going to give you data. You're going to graph it 3 different ways. Only one of your graphs should be straight. Whichever one is straight tells you the rate order of that data. Okay?
Yes.
Everyone kind of see how that works? Once again, when you do that, that might even make more sense. Yeah, Spencer?
What if it was just graphing A, but then it was like, I'm not sure how to explain it, but it looked like that graph should look. Then, so like say it looked like a natural log graph. Would you know that the function was a natural log because it looked like that on just a versus A?
Oh, yeah.
Because that's what I was thinking originally was what we were going to be doing. But
Yeah, you
Or
could do
like-
it that way too if you know like what it would look like. Yeah, that should be able to work. All right, the last thing here is this idea of half-life. We talked about half-life like last year if you took chemistry when you're talking about nuclear decay. This is very different. One really interesting thing about nuclear chemistry is you Like, so these things we talked about to speed up chemical reactions, they do not affect nuclear reactions at all. That's one of the crazy things to me as I contemplate it, is nuclear reactions, their rates are just their rate. Like the half-life of carbon is somewhere around 4,700 and something years.
For a certain isotope.
For carbon-12 or carbon-14. With that, there's nothing you can do or we can do to speed it up. You can't, if you heat it, cool it, crush it, it doesn't make nuclear things don't decay any faster. Which is why people talk about, that's why the storage of nuclear waste is such a problematic thing, is because you can't make it decay any faster. So when I'm talking about half-life here, we're not talking about like a nuclear half-life. All it is saying is it's the same idea. The half-life simply means is it's the time it takes for half of the sample to be gone. So if I started with 100 grams of my reactant, how long will it take to get down to 50? A really interesting relationship is that first order, and maybe circle that. Where does it say first order in here? Right here. Okay, circle first order, because this is unique to only first order reactions in the fact that their half-life is constant. And so it can be a really easy way actually to also identify something as first order, is if its half-life is constant, you know that it's first order reaction. Second order and things would not. So the generic, and this is actually on your formula sheet as well, to calculate the half-life of something, so T of 1/2, that's how you label it, is you simply take, there's two ways in which you can write it. You take the natural log, there's our ln, of 1/2.
Is that the negative?
The negative, sorry, yes, negative natural log.
I'm very confused about which order of reaction this is referring to, this thing you're drawing right now.
Those are left over from the last thing she did.
Oh.
Thank you.
Better? Okay, which, since that's just a number, technically if you plug it in, you get like 0.693 over K. So this is just a way you could calculate. If you know what the K is, you can find out what the half-life, like how long does it take to get to half my amount. But in general, this is kind of the biggest part, is that first order reactions, the concentration decreases by 1/2 at regularly spaced intervals. That it is also unaffected by how much I start with. So whether I start with 100 grams or 10 grams, it's gonna take the same amount of time to get to half the amount. So the initial has no effect, but that only applies to our first order reactions. Second order, we see that they depend more on that concentration, and so the speed will vary as the reaction progresses. So that half-life thing is particular to just first order reactions. Okay?
What about zero order reaction?
Zero order would also, their half-life is not constant.
Isn't it just like
Yeah, because if it's constant, then you get like an exponential. Because it's always about whether I go from 10 to 5 or 5 to 2.5, the time increments are always the same. Does that make sense?
Yeah.
Yeah, because it would be linear, but it's not.
half of it isn't decreasing at the same
Yeah,
rate?
exactly. Okay?
That makes sense.
All right.